Welcome in your own chemistry class. We are enjoying chemistry very well. We are studying here electrochemistry, and in this video we will discuss about the conductance and conductivities and the factors affecting conductance. Okay, first of all we will discuss about conductance. What is conductance? Students, as we have read Ohm's law. Ohm's law. What is Ohm's law? Ohm's law is V is equal to I R, or we can say I is equal to V upon R. This is followed by the all metal conductors. Metal conductors means in which electricity is conducted by the electrons. Means charge carriers are electrons in the metals. Okay, they follow the Ohm's law. I is equal to V upon R, or V is equal to I R, because there is very less resistance. Okay, but in electrolytes means the chemicals which can dissociate into cations and anions. In electrolytes, resistance is very much in the comparison of metal conductors. So we not measure the resistance of the conductors, but we measure the conductance of the electrolyte. So the conductance, as we know, more the resistance, less will be the electricity. So we can say more the resistance, less will be the conductance. Okay, so the conductance is the reciprocal of resistance. Okay, the reciprocal of resistance is termed as conductance. As we know, the unit of R is ohm. Okay, so the unit of C will be 1 upon ohm, or we can say ohm inverse, or mho. We can say mho. This is in CGS unit, but in SI system its unit is Siemens, denoted as S. Okay, clear? What is conductance? Conductance is the reciprocal of R. R means resistance. Clear? So see the conductance. The electrolytic conductors are follow Ohm's law. Also, according to Ohm's law, V is equal to IR, or I is equal to VR. But in electrolytes, resistance R is very high in comparison to the resistance of the metallic conductors. So in electrolytes, conductance is measured in place of resistance. So the reciprocal of resistance is the conductance. Hence the conductance is equal to 1 upon resistance R, or we can say C is equal to 1 upon R, and the unit of the conductance is mho, or ohm inverse, and in SI system its unit is Siemens. Clear, students? Okay, now we will discuss about conductivity or specific conductance. Okay, as we have discussed the reciprocal of R. Okay, reciprocal of yani resistance is equal to conductance. As in same way we know rho means specific resistance. Okay, so the reciprocal of specific resistance is known as the specific conductance, that is denoted here by small k. This is kappa. Okay, what is the kappa? This is specific conductance, or we can say it is conductivity. It was conductance. Kappa is specific conductance or conductivity. What is conductivity? It is the reciprocal of specific conductance. Now how we can calculate the formula for specific conductance or conductivity? Okay, see, as we know that R is directly proportional to L. L means the length of wire in metal conductance, but in electrolytic cells L is the distance between two electrodes. As it is voltmeter, these are electrodes, then the distance between the electrodes is L. R is directly proportional to L. More the distance, more will be the obstacles and more will be the resistance, and R is inversely proportional to 1 upon A. A means is the cross section of the electrodes. More the cross section, less will be the resistance. Okay, so we can say R is directly proportional to L upon A, or R is equal to rho L upon A. Clear? This is the rho, or we can say rho is equal to R into A upon L. This is the specific resistance or resistivity. So we are taking here the reciprocal of rho. Reciprocal of rho is equal to 1 upon R into L upon A. This will be reciprocal also. So this is the kappa. This is the C. And the ratio of L and A is known as X. X is the cell constant. So we can say specific conductance or conductivity is equal to conductance into X. X means cell constant. Clear? Kappa, sorry, conductance means ohm inverse, or we can say Simon. And X, what is X? L upon A. L means this is the ohm inverse. L means distance, this is centimeter. Okay, A is area. Area means centimeter square. This is cancelled by each other, so the unit will be ohm. Ohm inverse centimeter inverse. Okay, it is the unit of kappa, and in SI unit ohm is replaced by the S. Okay, ohm inverse, and centimeter inverse is replaced by the meter inverse. So in SI system its unit is Simon meter inverse. Clear? Now if L is equal to 1 centimeter and A is equal to 1 centimeter square. Okay, so kappa will be equal to C. Means when the electrodes are placed at 1 centimeter distance and the cross section of the electrodes is 1 centimeter square, then the conductance of the solution will be the conductivity or specific conductance. Clear? So see, the reciprocal of specific resistance or resistivity is known as the conductivity or specific conductance. It is denoted by the kappa, small k. We know that R is proportional to L and R is proportional to 1 upon A. So R is proportional to L upon A, or we can say R is equal to rho L upon A. Here rho is the resistivity or specific resistance. So rho is equal to R into A upon L. On taking the reciprocal of the equation, 1 upon rho is equal to 1 upon R into L upon A. 1 upon rho means kappa, 1 upon R means C or conductance, and L upon A is X. This is cell constant. So we can say kappa is equal to C into X. Here kappa is the conductivity, C is the conductance, and L is equal to cell constant. If L is equal to 1 centimeter and A is equal to 1 centimeter square, then kappa is equal to C. So we can say conductivity of the electrolytes is the conductance of the solution placed between two electrodes of 1 centimeter square cross sections at a distance of 1 centimeter. Okay, or we can say the conductivity of 1 centimeter square solution is called the specific conductance or conductivity of the solution. 1 centimeter square means, see, this is the unit distance and the cross section of this is 1 centimeter square. The total volume between the electrode will be 1 centimeter cube. So we can say the conductance of 1 centimeter cube solution, or 1 centimeter cube means 1 ml, is called specific conductance or conductivity of the solution. Okay, now see the unit of kappa. Kappa is equal to C into L upon A. C means ohm inverse, L is centimeter, A is centimeter square. Centimeter is cancelled by the 1 centimeter. So the kappa will be equal to ohm inverse, centimeter inverse, or in SI system ohm is replaced by the S and centimeter inverse is replaced by the meter inverse. So the unit is Simon meter inverse. Okay, now the new thing here is the cell constant. Now what is cell constant? See, cell constant, as we have seen in the for equation 2, the kappa is equal to C into X, means specific resistance or resistivity is equal to conductance into X, or we can say kappa is equal to C into L upon A. So the X, cell constant, is equal to L upon A, और वी कैन से x इज इक्वल टू, अगर कंडक्टेंस को इधर लेके जाएं तो कप्पा अपॉन c और कंडक्टेंस. ओके, द यूनिट ऑफ x विल बी x इज इक्वल टू l अपॉन a. l मीन्स centimeter. A means centimeter square. This is cutted by, so it will be centimeter inverse. And in SI unit, distance is measured in meter. So in SI unit, its unit will be meter inverse. Or on the basis of kappa into C, we can also calculate. Kappa means ohm inverse, centimeter inverse, and C means ohm inverse. Okay, this is cancelled by this, so the unit will be centimeter inverse, or in SI unit meter inverse. Okay, so the unit of cell constant is centimeter inverse or meter inverse. So we can define the cell constant, the ratio of L means the distance between electrodes, and A means the area of the cross section of electrode, is termed as the cell constant, or we can say the ratio of kappa and C. Kappa means resistivity and C means conductance, is known as the cell constant. Clear? Next term is molar conductivity, denoted by lambda m. M means molar. Molar conductivity. The conductivity was the conductance of the cell when the two electrodes are placed at 1 centimeter with cross section area of 1 centimeter cube. If the solution filled between the electrode is of 1 molar, 1 molarity, then the conductivity of the cell will be known as the molar conductivity. Okay, the conductivity of 1 molar solution, or we can say 1 mole solute, is called the molar conductivity, or the conductance of cell in which two electrodes of unit cross section area are placed at unit distance in 1 m solution. The most thing is 1 m, is known as the molar conductivity. Okay, if VML solution is present in the cell, so the lambda m will be is equal to kappa into V. Kappa means specific conductance or conductivity, and V is the volume. Here it is in liter, but we know that the molarity is equal to number of moles present in 1 liter solution, V liter solution. Okay, here 1 m means 1 mole is present in V ml solution. Ml means 1000 is multiplied here. Okay, so we can say V is equal to 1 is changed, now cancel the 1000 upon molarity. Okay, V volume is equal to 1000 upon molarity. So we can place this the value of V in the equation. So we can say lambda m is equal to kappa into 1000 upon molarity. Okay, now its unit. Kappa means ohm inverse, centimeter inverse, and molarity means mole per ml, or kahe 1 mole per centimeter cube. So centimeter cube is 1 centimeter cube is cancelled by this. So the unit will be ohm inverse, mole inverse, centimeter square, or in SI unit, ohm inverse is replaced by the S and centimeter square is replaced by the meter. So the unit will be Simon mole inverse meter square. Okay, and same is the equivalent conductivity, or lambda V, means when we take the solution of 1N in the cell between the electrodes of unit area cross section area and placed at 1 centimeter distance. Okay, the conductivity of 1 gram equivalent mass is called equivalent conductivity, or the conductance of cell in which two electrodes of unit cross section area are placed at unit distance in 1 n solution, is known as the equivalent conductivity. Thus lambda V, it is denoted by lambda V. Molar conductivity was denoted by lambda m. Okay, kappa is equal to V. Here V is the solution, ml of solution, but normality, here the concentration is taken in normality. Normality is equal to gram equivalent per liter. Here 1 n means gram equivalent is 1 into 1000 upon volume in ml, or we can say volume is equal to gram 1000 it is placed by the 1000 upon normality. So V is replaced kappa into 1000 upon normality. So lambda V is equal to kappa into 1000 upon normality. Okay, now its unit. lambda is equal to kappa into 1000 upon normality. Kappa means ohm inverse centimeter inverse. Okay, but normality is equal to equivalent per centimeter cube. Okay, centimeter inverse is cancelled by the centimeter inverse from here. So the unit will be ohm inverse centimeter square equivalent inverse, or Simon equivalent inverse meter square in SI system. Okay, clear this thing? Here are the units of the different terms. Conductance C, cell constant X, conductivity kappa, molar conductivity or equivalent, this is conductivity. Okay, units, conductance is ohm inverse, cell constant centimeter inverse, conductivity ohm inverse centimeter inverse, molar conductivity ohm inverse centimeter square mole inverse, and equivalent conductivity ohm inverse centimeter square equivalent inverse. In SI unit, ohm is replaced by the Simon and centimeter is replaced by the meter. So the SI units, conductance Simon, cell constant meter inverse, conductivity Simon meter inverse, molar conductivity Simon meter square mole inverse, and equivalent conductivity Simon meter square equivalent inverse. Okay, see one example of this type. At 25 degrees Celsius, a conductivity cell containing 0.001 m KCl solution has a resistance of 1500 ohm. Its conductivity of 0.001 m KCl is 0.146 into 10 to the power minus 3 Simon centimeter inverse. Then find the cell constants of the conductivity cell. Cell constant means conductivity upon conductance. This is conductance. Okay, here conductivity is this, and conductance can be calculated by 1 upon R. So 1 upon 1500. So here kappa is equal to this, conductance equal to 1 upon R. Okay, then X will be equal to 0.146 into 10 to the power minus 3 Simon centimeter inverse upon 1 upon 1500. So the answer will be 0.219 centimeter inverse. Okay, clear? One more example, the conductivity of a 0.05 m solution at 298 Kelvin is 0.001 ohm inverse centimeter inverse. Calculate the molar conductivity. Molar conductivity lambda m is equal to 1000 into kappa upon m. 1000, kappa is 0.001. Okay, and the molarity is 0.5. Place the values and calculate. The answer will be 20 ohm inverse centimeter square mole inverse. Next example, resistance of a 0.0005 n NaOH solution is 31.6 ohm. This is the R. Cell constant X is the 0.357 centimeter inverse. Calculate the conductivity and equivalent conductivity. Okay, normality is given, R is given. So conductivity kappa is equal to 1 upon R, conductance, into cell constant. 1 upon R is 1 upon 31.6 and cell constant is 0.357 centimeter inverse. So the conductivity will be 0.0113 ohm inverse centimeter inverse. Okay, now equivalent conductivity lambda is equal to kappa into 1000 upon n. Kappa is calculated here 0.0113. Okay, into 1000 upon n. N is given 0.05. So the lambda V or equivalent conductivity will be 226 ohm inverse centimeter inverse equivalent inverse. Clear? Now we will discuss the factors affecting conductance, only conductance. Okay, conductance of the electrolyte is depend upon the number of ions. More the ions, more the charge carriers. More the charge carriers means more the conductance. Okay, so we can say conductance C is directly proportional to number of ions. The factors affecting the number of ions means degree of ionization, okay, will also affect the conductance. Okay, so first of all we will discuss about dilution. Dilution is directly proportional to conductance. Okay, conductance. Why? We know on dilution degree of dissociation increases. Degree of dissociation, or we can say degree of ionization increases. degree of ionization increases, so the number of ions increases. Number of ions increases, so the conductance also increases. Clear? Dilution increases, ionization increases. Ionization increases, number of ions increases, so the conductance also increases. Okay. Second factor is nature of electrolytes. ठीक है, nature of electrolytes are, so first of all I am explaining you what is first of all matter. On the basis of dissociation is divided in two parts, electrolytes and non-electrolytes. Okay, non-electrolytes means does not dissociate, do not dissociates, like glucose does not dissociate, urea, sugar, these are the non-electrolytes. Okay, electrolytes means dissociation occurs, okay. On the basis of the extent of dissociation, these are divided in two parts, strong electrolytes and weak electrolytes. Strong electrolytes means 100% ionization हो जाता है. Weak electrolytes means less than 100% ionization occurs. Okay, less than 100% ionization occurs. These are weak electrolytes. These are acids, bases and salts. Okay, strong electrolytes, strong acids. Acids means HCl, HNO3, H2SO4, etc. Bases means NaOH, KOH, etc. Weak acids like HCN, CS3, COOH, etc. Weak base like ammonium hydroxide, okay, barium hydroxide, etc. These are the weak bases. Weak means these are not dissociated 100% and strong means dissociated 100%. Okay, so electrolytes, strong electrolytes means more dissociation. More dissociation means more number of ions. More number of ions means more conductance. Weak electrolytes, more degree of dissociation is less. Degree of dissociation less, then number of ions less, so the conductance will be less. Okay, nature of solvent. Three factors of solvent affect the number of the degree of dissociation and conductance also. First of all, nature of solvent में polar और non-polar. Polar means more ionization occurs. More ionization occurs, conductance increases. Non-polar means less ionization. Less ionization, the number of ions are less, so the conductance will be decreased. Viscosity of solvent is inversely proportional to conductance. More viscosity, more friction between the ions. More friction between the ions, more the obstacles. More resistance, and more resistance means conductance is decreased. Solvation. Solvation means the interaction between solvent and solute. Okay, more attraction, the attraction forces between solute and solvent and solute is known as the solvation. More attraction forces, more solvation. More solvation, then the mobility of the ions is decreased, and the mobility of ions is decreased, then conductance is also decreases. Clear? These three factors of solvent affect the conductance of the electrolyte. Next factor is temperature. Temperature is directly proportional to conductance. Why? As temperature increases, degree of ionization increases. As degree of ionization increases, number of ions increases, so the conductance also increases. Okay, clear? Thus these four factors affect the conductance of the electrolytes. Thank you.